Chapter 9 Scrutiny. You get what you need in both life and business. Quotes: The mind does not pay equal attention to everything it perceives, for it applies itself infinitely more to those things that affect it, that modify it, and that penetrate it, than to those that are present to it, but do not affect it. By Nicholas Malebranche, The Search After Truth. Our senses forays for fitness, not truth. They dispatch news about fitness payoffs, how to find them, get them, and keep them. Despite their focus on fitness, our senses confront a tsunami of information. The eye sports 130 million photoreceptors, which collect billions of bits each second. Fortunately, most of those bits are redundant. The number of photons caught by a receptor differs little, in general, from the number caught by its neighbors. The circuitry of the eye can, with little loss in quality, compress those billions of bits down to millions, just as you may, with little loss in quality, compress a photo. It then streams the millions of bits to the brain through the optic nerve. This stream, though compressed 1,000-fold, is no gentle brook. It is a flood, which would overwhelm the visual system if untamed. Taming this flood is the job of visual attention. Billions of bits enter the eye each second, but only 40 win the competition for attention. The initial descent from billions of bits to millions loses almost no information, like a book manuscript edited to omit needless words. But the final plunge to 40 loses nearly everything, reducing the book to a blurb. This blurb must be tight and compelling, just the essentials to forays for fitness. This may feel at odds with your experience of visual world that seems packed from corner to corner with myriad details about colors, textures, and shapes. Surely, it would seem, we see more than just a headline. We see articles, editorials, classifieds, the whole works. But our experience deceives us. Consider the two images of Dubai in figure 25. They are identical, except for three major changes. Try to find them. For most of us, it takes a surprisingly long time. A phenomenon known as change blindness, underquotes. We hunt in vain until we happen to stumble upon a difference, whereupon we can't help but see it thereafter. There are many examples online of change blindness, which will entertain you as they demonstrate that it is an important and general aspect of human vision. Figure 25, change blindness. There are three differences between these two images. Try to find them. What is going on here? Vision forages for fitness, but the foraging process itself, to be fit, must be lean and only deploy its meager resources with discretion. Countless messages about fitness impinge on the eye like 1,000 emails flooding in an inbox. The visual system does not waste time and energy reading them all. It treats most of them as spam and deletes them immediately. It selects a precious few to read and act on. Getting unwanted email on your smartphone is a nuisance, and calling it is a chore. But with vision, the stakes are life and death. One who attends to the frivolous while missing the vital will forfeit becoming an ancestor. Natural selection ruthlessly shapes our visual attention to a nimble forager. To cut billions of bits to 40, the visual spam filter is ruthless about deletion. It follows simple and fascinating rules. For those deployed in the trenches of marketing and product design, knowing these rules is essential to success in the ubiquitous battle for the ephemeral attention of consumers. Those who master the rules can direct attention to their products and away from the competition. Those less versed in the rules risk inadvertent altruism. The opening gambit of the visual filter is its placement of photoreceptors. Unlike the sensor of a digital camera, whose pixels are equally spaced throughout, the retina of the eye deploys more photoreceptors in the center of vision, and even fewer toward the periphery. Most of us assume that we see the whole field of vision in rich detail, but we're wrong, as figure 26 demonstrates. If you look at the dot in its center, then you will see that smaller letters in inner rings are as easily discerned as larger letters in outer rings. To be equally legible, the letters in outer rings must be larger, because there the density of your receptors is lower. Figure 26, visual acuity. If you stare at the middle dot, the big letters are as clear as the smaller. As you can see from the figure, the density of photoreceptors drops rapidly. Indeed, although our visual field extends 200 degrees horizontally and 150 degrees vertically, we enjoy high resolution in only the 2 degrees that surround the center of gaze. The visual width of your thumb when you see it extended at arm's length is 1 degree. As I mentioned earlier, staring at your thumb on your outstretched arm brings home how tiny your window of detail really is. Its area is 10,000 times smaller than your field of vision. Why is it, then, that most of us never notice this limit of vision and mistakenly believe that we see the whole field of vision in high resolution? The answer lies in the incessant movement of our eyes. They look and jump about 3 times a second, more when you read, less when you stare. The looks are called fixations and the jumps are known as saccades. Each time you look at something, you view it through a tiny window replete with detail. Normally, you don't look and see a blur. So we find it natural to assume that we see everything at once in great detail. The placement of photoreceptors is part of an inspired strategy in the quest for fitness. The wide field of vision, with its low resolution, is used to hunt for possible messages about fitness. A flicker over there on the left might be the twitch of a tiger's tail, and that twinkle over there on the right might be water. These possibilities are ranked for importance. Better check for a tiger before checking for water. Then your eyes look directly at each item in order so that each is seen in high resolution and analyzed in enough detail to decide what to do next. That flicker turns out to be just a leaf in the wind, not a tiger. So forget it and move on. That twinkle turns out to be water. Time to get a drink. Why do we suffer from change blindness? Why do we struggle to find the differences between the 2 images of Dubai? Because we forage for fitness. We search for the visual field for a message about fitness that may be worth the effort to examine in detail. Most messages aren't worth this effort. Natural selection has shaped us to ignore them. If we ignore them, then we are unlikely to notice if they change. Change blindness is not a failure to see the true state of objective reality. It's a choice to discard news about fitness that's unlikely to alter our fitness. Figure 27. Pop out. We easily see large 2 in the left box, the lighter 2 in the middle box, and the tilted 2 in the right box. For those readers interested in marketing and business, this idea applies to visual advertising. The goal of successful advertising is not merely, and sometimes not even, to present important facts. It is to craft a visual message that rivets the foraging eye of the typical shopper. Consumers face a chaos of competing messages. The trick is to grab their attention. At the simplest level, a message can grab attention by differing from its neighbors in color, size, contrast, or orientation. For instance, in figure 27, going from left to right, what grabs attention is the larger 2, the 2 of different contrast, the 2 with a different orientation. In these examples, the item that is different grabs attention quickly, even if many items surround it. For instance, in figure 28, the green 2 pops out when there are few distractors, as in the image on the left, but also when there are many distractors, as in the image on the right. Figure 28, color pop out. The green 2 is easily seen even when surrounded by many black 2s. But some differences don't pop out. In figure 29, the 5 is hard to find and gets harder with more items around it, as in the image at the right. Figure 29, difficult search. The 5 in each boxes does not pop out. One must search for it. Similarly, in figure 30 on the left, it is hard to find the cross. And in the figure 30 on the right, it is hard to find the T that is gray and upright. Figure 30, difficult search. The cross in the left box and the gray upright T in the right box do not pop out. Some visual cues, color, size, flicker, motion, contrast, and orientation can pop out of visual clutter and into attention. They are called exogenous cues under quotes because they can arrest attention even if we're not searching for them. A careful photographer understands their power and edits photographs to remove pop-outs that distract from the main subject. No bride wants to be upstaged in her photos by a stray line or a high-contrast knick-knack that loiters in the background and lures the eye away. The edge of a photograph can itself pop out if it has high contrast. Photographers will sometimes vignette a photograph, gently darkening it near its edges to remove this distraction and keep the eye on the central subject. Managing the power of pop-out is critical to success in advertising. Every ad, without exception, dictates a foraging strategy for the eye of the viewer. Does your ad send the eye on a goose chase? Or does it guide the eye to glean the facts and emotions you wish to convey? If we think that vision is just a camera that records objective reality, then we misunderstand what really happens when someone views an ad. Think instead of vision and all our senses as foraging instruments evolved by natural selection to hunt for critical information about fitness. Figure 31 shows a display at the entrance to a sportswear store in an upscale mall. It peppers the eyes with sight-tracking cues. Most egregious are the bright reflections on the window in the upper left and upper right, and lesser reflections scattered throughout. Their contrast in brightness and color lures the eye to dead ends. When the viewer walks, the reflections slide along the window, and this motion adds to their pointless lure. The cure is reflection-free glance. But even without reflections, this display echoes with spurious cries from all quarters of a visual jungle. There is a rainforest, 2 Jackson Pollocks, a wall of non sequitur orange, stark highlights on bald heads of stiff mannequins, and on the left, hanging by one hand, a dangling modifier. All pointless distractions. There is, if you look closely, a key message. On the quotes, quick drying and vented for any activity, closed quotes. T-shirts on mannequins meant to be the stars languish in obscurity for lack of light and contrast. If vision, like a camera, recorded each detail, then this display might succeed. But the data are all there. But vision is no passive camera. It is an impatient hunter for fitness payoffs. It may hazard an unrewarded glance or two at this display, but then give up and move on long before it chances on the key but hidden message about drying and venting. By contrast, the famous ads for iPods expose all needless pop-outs. In these ads, the background splashes a bold but uniform color. The foreground sports an ecstatic dancer in black silhouette devoid of all features, save one. White earbuds sprout white wires that sweep, carefree, down the black silhouette and converge into a white iPod grasped by a gyrating black hand. The emotion is contagious. No words needed, no words used. The message for fitness is clear. iPod equals ecstasy. Any questions? In our visual search for a message deserving attention, we group messages that have common themes, making them easier to attend or discard en masse. For instance, the 16 dots on the left of figure 32 can be grouped based on contrast into rows, as in the middle, or into columns, as on the right. They can be grouped by color, as in figure 35. They can be grouped by orientation, as in figure 36. They can be grouped by proximity, as in figure 37. The list omits other potent features such as flicker, motion, and depth. Competing features can promote competing groups. In figure 38, on the left, orientation and proximity cooperate to create horizontal groups. But on the right, proximity overrides orientation and dictates vertical groups. Grouping assists the search for outliers. In part A of figure 39, it takes effort to find the maverick line segment, but you rearrange the segments to promote grouping, as in part B of figure 9, and the outlier pops out. This technique applies to in-store merchandising. A shelf of products can present the shopper with a bewildering mess, but with clever grouping of colors, contrasts, and other features, that shelf can offer happy hunting. Grouping is a form of data compression. For instance, each line segment in figure 39 has an orientation, and in part A of figure 39, the visual system is forced to describe the orientation of each segment, one at a time. But in part B of figure 39, the visual system can make its description much more compact. The 18 segments on the left are horizontal and the 18 segments on the right are vertical. Except for one at a slant, grouping lets one description apply to an entire group. No need to repeat the description ad nauseum for each item in the group. This compression helps us find pertinent changes. In part B of figure 39, the slanted segment pops out. Attention is yanked by exogenous cues, but it can be bridled to track endogenous goals. If you search for a lemon, then all things yellow becomes more salient, aiding your search. Neural activity in area V1 of your brain's occipital cortex correlates with saliency and with its modification by goals. Nearby neurons signal nearby points in the visual world so that the whole collection of V1 neurons forms a topographic map of the visual world, a salience map. A neuron actively responding to a feature such as a color inhibits nearby neurons if they too are responding to that color. This lateral inhibition reduces the salience of those features more common in the field of view and enhances the salience of the rare. An endogenous goal, such as finding an orange, alters this salience map by enhancing the activity of neurons that respond to features relevant to the goal. If, for instance, you look for black in figure 40, then a field of black axis occupies your attention. If instead you look for a white, then a field of white O's enters your attention and a white X pops out. If your goal is to check for a tiger hiding in the bush, then your target displays a variety of colors. If you pick the wrong color to enhance in your map of salience, your mistake could end your life. So natural selection has shaped us to enhance colors intelligently. The yellows of the tiger, which match the colors of the brush, are the wrong choice because enhancing them does little to distinguish the tiger from brush. Instead, you astutely enhance the distinctive oranges of the tiger, helping the tiger strives to pop out visually from the brush, so that the tiger won't pop out viscerally onto your torso. Enhancing the right features of your target does not, however, guarantee that it will pop out from the scene. You may need to search a bit before your eye naps your visual query, say predator or prey. If you can search quickly, you are more likely to find your prey in time to put it on your menu, or to find your predators in time to cross yourself off theirs. For this reason, natural selection has shaped your search to be efficient. Your eye looks only to regions rich in distinctive features of your target, and it rarely looks back. If you check a spot and find no target, then your visual system remembers the spot and doesn't usually send your eye on the fool's errand of returning to that same spot. This handy trick is called Inhibition of Return, under quotes. It is handy but not infallible. Suppose you are hungry and searching for a ripe apple. Your visual system duly enhances those regions of your salience map that exhibit the distinctive features of such an apple, say its red color. Then it picks the spot in your visual field that has the most salience. It directs your eye to look at that spot, to place it in the small window of detailed vision. Then it decodes the fitness messages that it finds there. Suppose that the resulting message is red leaf. That could be a useful message if, say, you are looking for tinder to start a fire. But you're hungry and you want an apple, so red leaf doesn't quite fit the bill. Your visual system diligently triggers its inhibition of return trick so that it won't stupidly revisit that leaf, and then sends the eye to the next spot of interest, the spot with the second most salience. Suppose there it finds a red rock. Not an apple. No need to check there again. Inhibition of return. Everything so far is going swimmingly. On to the next spot. Decode the new message. Tiger. Not an apple. No need to check there again. Inhibition of return. Whoops! If what you see is not what you seek, then in most scenarios, inhibition of return is a smart move. But here it could be your last mistake. Tiger isn't the message you sought, but it's a message you can't ignore. And not just tiger, but any message involving predators or prey. If a hunter-gatherer seeks an apple and instead spies a hoof or paw, then inhibition of return is the wrong move. In short, if I see an animal, be it predator or prey, then I should stop my search for an apple or whatever I am seeking and instead monitor what is mobile. This logic persuaded evolutionary psychologists Joshua New, Leda Cosmides, and John Tooby to propose in 2007 that we evolved an, under quotes, animate monitoring, closed quotes, system. It is designed to detect and monitor any animal in the visual field. The attentional processes that we have discussed so far, based on exogenous cues and endogenous enhancements, rely exclusively on low-level features such as color, shape, and flicker. The animate monitoring system, by contrast, is tuned not to low-level features but to a category of objects, animals. New, Cosmides, and Tooby tested their proposal using change blindness experiments. On each trial, an observer saw a blank screen. Then, for a quarter of a second, a photograph of a complex natural scene. Then a blank screen, then the same photograph again, but with an important change. An object was deleted. This sequence of frames kept repeating until the observer detected the change. To keep observers honest, 1/3 of the trials were cat's trials, in which there was no change. On some trials, the change was to an animate object, a person or an animal. On other trials, the change was to an inanimate object, a plant, a movable artifact, such as a stapler or a wheelbarrow, a fixed artifact, such as a windmill or a house, or a vehicle, such as a car or a van. As predicted, observers detected a change to an animate object more quickly than to an inanimate object, on average 1 to 2 seconds more quickly, a significant speed up. One may wonder if the price of more speed is less accuracy. Hasty can mean sloppy. To the contrary, observers missed only 1 in 10 changes to animate objects, compared with 1 in 3 to inanimate objects. We're faster and more accurate at detecting animate objects for good evolutionary reasons. In modern urban environments, vehicles are more common and dangerous than animals. Nevertheless, observers are faster and more accurate at detecting changes to animals than to vehicles. This is to be expected if animate monitoring was wired into us by evolution long before the advent of vehicles. Our eyes forage for fitness today using strategies that our ancestors evolved during the Pleistocene, a geological epoch marked by repeated glaciation stretching from 2.5 million years ago to just 11,700 years ago. We can exploit these ancient strategies to design modern marketing. Suppose you sell soap in an orange bottle, and a shopper strolls by, looking instead for a competitor's blue bottle. She glances at a bottle and determines that it's not the color she seeks, flings a dollop of Inhibition of Return at your shelf of orange bottles, and henceforth ignores your product. That helps her search and hurts your sales. What to do? How can you disrupt her search for a blue bottle and focus her invaluable attention on your orange bottles? You could trigger her animate monitoring system. One way would be to stamp, say, a cat or a deer on your bottles. This could work, but it's far from subtle, and once the competition caught on, they could slap some animal on their bottles and erase your competitive edge. To be more subtle, you can dispense with flaunting a beast in toto and opt instead to reveal some part, an eye, a hand, a paw, a face. A glimpse of an eye is, for purposes of triggering the animate monitoring system, a glimpse of the beast peering through that eye. Natural selection has made it so. One who attends to a beast only when seen in its entirety risks missing a potential or becoming an actual meal. A message that says "I" also says that there is a creature who owns that eye and warrants your attention. This advertising strategy, use part of the animal, not the whole, is indeed more muted, but still not subtle enough. The competition will figure it out. The logic of evolution suggests a better strategy. It takes time to verify that what you see is an eye. If you take too much time on verification, you may fail to act in time to catch a meal or to avoid becoming one. So natural selection favors shortcuts. Anything remotely like an eye wins attention, if only briefly. The male jewel beetle, you will recall, is lax about what constitutes a significant other. He is just as happy with a glossy bottle as he is with a female beetle. A male moose is tantalized by either a female moose or a bronze bison. A herring gull chick seeks sustenance from its mother or from a rectangle of cardboard sporting a red desk. A grey-lag goose is content to sit on its own eggs or to try its luck with a volleyball. A male stickleback intent on defending its territory will fight another male, or it will fight a piece of wood with a shape unlike a fish if it is painted red underneath. Ethologists have a treasure trove of such examples. Natural selection routinely shapes perception to deploy categories that are loose. This opens a world of possibilities, now largely untapped, for disruptive innovation in marketing and advertising. The eye of the shopper, like that of the beetle and moose, counts on shortcuts and tricks to guide its attention. Those who know its heuristics can lure it all with well-crafted icons. The trouble and opportunity is that little is known of the tricks and shortcuts deployed by human vision to detect animate objects. What simplified icons can still trick the shopper to see, if just for a moment, a face, a hand, an eye, or a butterfly? We don't know. Several years ago, I was strolling down an aisle in a store, and my eyes were suddenly riveted by a bottle of shampoo sporting an annulus that sparkled with iridescence. The exogenous cue of sparkling, no doubt, grabbed my attention, but I found that I persisted in gazing at that annulus. Perhaps a sparkling annulus says "I" underquotes to the part of vision that triggers the monitoring of animals. What other simplified icons for eyes might trigger such monitoring? And not just icons for eyes, but for the variety of bodily parts of humans and other animals? To answer these questions, we must reverse engineer with careful experiments the heuristics that natural selection has wired into human vision. I have understated the real potential here. The jewel beetle doesn't just like a beer bottle as much as a female, he likes it far more. The herring girl chick doesn't just like a cardboard cum disc as much as its mom. As the disc gets bigger, he likes it far more. A stickleback doesn't just fight a red-bellied bob as much as another male. As the fox belly gets bigger, he will ignore a real male to fight the harmless blob. A male Homo sapiens doesn't just like a female with breast implants as much as a female au naturel. If the implants impart an upper convexity not seen in nature, he likes it far more. A caricature of a face isn't just identified as well as a photograph, it is identified more quickly. These are examples of, underquotes, supernormal stimuli. Evolution shapes the perceptions of an organism to track fitness, not truth, as cheaply as possible given the demands of its niche. Supernormal stimuli hint at the resulting codes for fitness in its niche. A herring gull chick can succeed with a simple code. A larger red disc means a better chance for food. The implications for marketing are clear. A simple icon, crafted to exploit the visual codes wired by natural selection into the visual systems of consumers, can grab attention with supernormal power. Such an icon can be subtle and thus difficult for a competitor to reverse engineer, and yet highly effective. For icons used in branding, emotional import is also critical. The goal is not just to grab attention, but to grab the right kind. This typically requires an icon that associates with the brand a specific positive feeling, say prestigious and wealthy, or rugged and healthy. An icon that brandishes fangs will grab attention, but apart from ads for vampire movies and Halloween costumes, attention of the wrong kind. A well-crafted icon can exaggerate judiciously visual features that draw attention and trigger a desired feeling. Suppose, for instance, you want an icon of an eye that grabs attention and feels attractive. Recall from Chapter 2 that a female eye looks more attractive if it features a large iris, a dilated pupil, a bluish sclera, conspicuous highlights, and a prominent limbal ring. There are surely other critical features of an attractive eye not yet discovered. The challenge for a marketing team is to create an icon, perhaps a stylized eye or something more abstract, that captures such features with supernormal effect. At present, given the limits of our scientific knowledge, this challenge may best be achieved through the intuitions and talent of a graphic designer. But a corporation that conducts experiments guided by evolutionary theory to learn how to hack the visual code of Homo sapiens for the attractiveness of eyes could exploit its knowledge to create icons that manipulate this code to powerful effect. This is just one example in a vast and largely unexplored territory. One-third of the brain's cortical activity is, as we have discussed, correlated with visual perception. If you include the other senses, there's lots of sensory coding to explore and hack. Some of it, perhaps most of it, is spaghetti code, as inelegant as the unintelligent design of our eye, with its photoreceptors stupidly cloaked behind neurons and blood vessels. Our perceptions are a species-specific user interface, not a window on truth, and its underlying code is a sea of kludges, punctuated by islands of inadvertent brilliance. Vision does not approximate an ideal observer who recovers objective truths. It is an interface sloshed together on the chip. It tells us just enough about fitness to keep us alive in our niche long enough to raise kids. Understanding this and letting it guide our choice of experiments is a promising direction for perceptual science, marketing, and product design. Our interface is wired to detect and monitor predators and prey. The logic of selection that installed this wiring is, we have seen, clear and compelling. Those with the wiring are more likely to enjoy lunch than to be lunch. Meat, however, was not alone on the menu of Homo sapiens. We are omnivores, not just carnivores, and our ancestors have long eaten fruits and vegetables. Has natural selection wired us to detect fruits and vegetables, and since they are immobile, to remember where they reside? The evidence for preferential detection of fruits and vegetables is, at present, equivocal. The experiments by New, Cosmides, and Tooby, which found quick detection for animate objects, found otherwise for plants. However, the plants they tested were trees, shrubs, and a pineapple. No experiment to date has studied whether we are specially tuned to detect fruits and vegetables. The recent evolution of trichromatic vision in primates, which allows finer discrimination between reds and greens, may have been selected in part to aid the detection of ripe fruit against green foliage. This hypothesis, though intriguing, is for now controversial. However, Joshua New and his colleagues found in an experiment that took place at a farmer's market that we remember well the locations of foods, and we remember better the location of a food that is higher in calories, even if that food is not well liked. Moreover, women remember better than men. This makes sense. Memory, like perception, evolved in service of fitness. Our memories are no more a veridical report of the past than our perceptions are of the present. Memory and perceptions don't deal in objective truths. Both deal in fitness, the only coin of the evolutionary realm. It is no surprise that fruits and vegetables that offer more fitness receive more memory. This suggests that an icon of food can enhance our memory for a product just as an icon of an animal can enhance our attention to it. Care must be taken, of course, to fashion an icon that succeeds at hacking into our visual code and masquerading as a high-fitness food. Get it wrong, and an icon can brand a product as unpalatable and unmemorable. Get it right, and an icon can go supernormal. Add a chromature of high-end food, such as a honeycomb, and it may make the memory much stronger. Let's recap. Our eyes are reporters on the fitness beat, searching for a scoop, looking for intelligence about fitness that is worth decoding. A message, once decoded, typically appears in a standard format. We see the decoded message as an object in space whose category, shape, location, and orientation inform us how to act to glean the fitness points we need. We gumshoe for fitness on the cheap, attending to just a fraction of the leads on offer. Exogenous cues can grab our attention: depth, flicker, and movement, contrasts in size, color, brightness, or orientation. Endogenous goals can alter the salience of the exogenous cues. Looking for a pear makes its distinctive green more salient. We constantly scan for anything animate. We may also scan for high-calorie foods. This repertoire of strategies in our search for fitness payoffs makes the process of searching itself more fit. But we have another technique in our repertoire: scripted attention. Its impact is best described by example. I was asked by a major jeans company to evaluate their new print ad. It prominently displayed a buff man wearing jeans and a winning smile. This is a good move because it triggers in shoppers the module of attention that monitors people and animals and associates with the brand the positive attributes of robust health and upbeat mood. The ad splashed the company logo in bright color and high contrast, a good way to grab attention with exogenous cues. But the ad, to its detriment, misdirected the attention of the shopper because it missed the role of scripted attention. Here's how. We are a social species. When you forage for fitness, you note where others forage. Where they attend, you also attend. After all, what grabs the attention of another person may warrant your attention as well. Perhaps they see vital information about fitness that you missed. A stalking lioness, a delicious morsel, a helpful friend, an implacable foe. You infer from the direction of their body, face, and eyes where they attend, and you shift your attention to match theirs. In the jeans ad, the body, face, and eyes of the model all aimed one direction, away from the logo and into empty space. The model turned his back on his own ad. His body from head to toe told the shopper a clear message. Forget this product. There's something of greater interest over there on the left. If, by chance, on the left there was an ad for the jeans of a competitor, then the model would unwittingly tell shoppers that the competitor's jeans deserve more attention than his own. This is not the best use of marketing dollars. Fortunately, this was easy to fix. I swapped the two sides of the ad so that the model directed attention where the jeans company wanted it, on their logo. This is an example of scripted attention. We use our knowledge of our current context to constrain how we forage for fitness, allowing us to forage with greater speed and precision. In the context of viewing a person, our script leads us to attend where the person's face and body appear to be focused. We deploy other scripts for attention. In a store, you don't search for products on ceilings or floors. You just attend to shelves. In your bathroom, you know where to look for soap and razor. If you're driving in the US, then you glance left before turning right. In the UK, you do the opposite. If you fly from the US to the UK and rent a car, good luck. Your scripts, I can attest, dispatch your attention to random places, risking mayhem. A script for attention that buoys fitness in one context can scuttle it in another. Natural selection shaped us the capacity to learn new scripts. As the environment changes, we can alter our scripts. Our script for people directs us to follow their gaze, but it does more. It directs us to look at hands. What is that hand up to? Where is it pointing? What is it holding? A weapon? Food? The hand of another person can, in an instant, alter your fitness for better or worse. Attending to hands is itself a fit strategy. In the jeans ad that I evaluated, the hands of the model did nothing to promote the product. They just dangled. If instead a hand is made to hold a product or gesture toward a logo, then that hand can assist in directing attention. Standard accounts of attention assume that objective reality consists of cats, cars, and other physical objects in space and time, and that attention directs us to look at and to accurately perceive these pre-existing objects. This assumption is false. Cats and cars are messages about fitness in the sensory interface of Homo sapiens. When I look from cat to car, I don't switch attention from a pre-existing cat to a pre-existing car. Instead, I decode one fitness missive and get the message cat. Then I decode a second missive and get the message car. I create and then destroy cat and car and the other objects as needed in my endless foraging for fitness. Fitness functions are complex, depending on the organism, its state, its action, and the state of the objective world, whatever that world may be. Some aspects of fitness are stable. That is why I can see my cat Tulip, look away, then look back and see her again. I see the same Tulip because I decode the same missive about fitness. Some aspects of fitness are transitory. If I take a step to the side and then look again at Tulip, she looks a bit different, a bit rotated. If I eat 2 hamburgers, a third hamburger doesn't appeal to me quite as much as the first 2. These variations in my perceptions of cat and burger reflect variations in the fitness that these objects encode. I love my cat and enjoy my car, but I don't believe they exist if unperceived. Something exists, whatever that something is. It triggers my senses to acquire a coded message about fitness in an idiom of cats, cars, and burgers, the parlance of my interface. That vernacular is simply inappropriate to describe objective reality. I love the sun and don't want to part with my neurons, but I don't believe the sun existed before there were creatures to perceive it, or that my neurons exist if unperceived. Stars and neurons are just icons in the space-time desktop of my perceptual interface. If our senses were shaped by natural selection, then our perceptions do not portray true properties of objective reality, any more than the magnifying glass icon in my photo editing app portrays the true shape and location of the real magnifying glass inside my computer. When I click on that icon, my photo enlarges. If I ponder why it enlarges, I may conclude that the icon is the cause. I would be wrong. My mistake is a harmless and even useful fiction, as long as I just edit photos. But if I want to build my own app, then this fiction is no longer harmless. I need to understand a deeper level of cause and effect within the computer that is hidden by its interface. Similarly, for most research and medical applications, it is a harmless and even useful fiction to think that neurons have causal powers, that neural activity causes my thoughts, actions, and other neural activity. But if I want to understand the fundamental relationship between neural activity and conscious experiences, then this fiction is no longer harmless. I must understand a deeper level of cause and effect that is hidden by the space-time format of my sensory interface. The reason that my perceptions can show me the truth, can show me the sun in itself, is that the sun in itself is shrouded by a cloud of fitness payoffs. The cloud determines my fate and the kismet of my genes. Evolution has steadfastly directed my perceptions to the cloud of fitness payoffs, not to the sun in itself. The sun in itself affects the cloud and, in consequence, my perceptual experience as of the sun. But my perceptual experience as of the sun does not describe the sun in itself. A computer file affects its icon on the desktop, but its icon does not describe the file. Our perceptions of objects in space-time are not objective reality, the thing in itself, nor do they describe it. Does this mean that objective reality is forever beyond the reach of science? Not necessarily.